Welcome back, everybody. 10.3, we're taking a look at our next advanced algorithm. We're going to take a look at another sorting algorithm. Okay, this one's called Insertion Sort. Let's just get into it and show you what it is. All right, now let's kind of talk you through Insertion Sort before we go through the code. Okay, Insertion Sort's very similar to the way that people sort things in real life. It's a very natural algorithm for it. What I'm going to do with Insertion Sort, instead of running through this entire list and looking for the smallest element in the whole thing, I'm just going to start off at the beginning of the list with the 9 and the 2, and I'm going to make sure they're in the right order. Okay, my next step, I'm going to go with just one more up, the 8, the 2, 9, and the 8. I'm going to make sure that chunk of the list is in order. So I'm going to put the 8 in the right spot. Okay, where the word insertion comes from is that each time I step to the next index of my list, in this case the 5, what I'm going to do is I'm going to track back and insert it in its proper spot. So the 5 should go between the 2 and the 8. I'm going to insert it there and kind of shift everything else down the line. Okay, same thing with the 7. We'll insert that in the right spot. Okay, there's some more details to it. There's some more steps that happen in between there, but that's the basic idea. It's actually a pretty easy sort to do by hand. It's pretty simple to kind of get the steps of insertion sort in the right order. All right, so let's talk you through the code here. Okay, here's one way we could implement insertion sort. So again, we have a void method. We're not returning anything. We're just going to sort, in this case, an array list of integers called nums. Now we could apply the same algorithm to just the normal array. We could have different types stored in that array, but we'll do an array list of integers here. And we have two loops again, outer loop and inner loop. The outer loop's going to loop from index 1 through the entire loop to the size to the end of the array. We'll explain why we're starting at 1 instead of 0 in a second. And each time through the loop, we're going to store whatever is at index I in a variable called val, and then set the counter for the inner loop, the j, equal to the I to start off with. Now I've got to do that outside the loop header because for the inner loop, we're going to use a while loop this time. And what the while loop's going to do is it's going to run as long as j, our inner loop counter, is greater than 0, and value, kind of the current value we're looking at, is less than nums at j minus 1. In other words, less than the previous value in our array. Okay, the reason, again, I have to start off with index 1 instead of 0 is since I'm comparing it to 1 less. Okay, if I'm 1 less than 0, I'm out of bounds. Can't do that. And as long as this loop runs, we're going to do something pretty simple. What we're going to do is just set what's in the array at j to what's at j minus 1. So in other words, the previous value. Because from this loop, we confirm the previous value is greater than what's at j. And then we're going to count down j by 1. Okay, so we'll continue going backwards with my values of j. As long as I can go backwards, j is greater than 0, and the previous value, the value before j is less than j, we'll keep on shifting everything up 1, and then once that's no longer true, we'll be done with the loop, and we'll set the new j equal to the value we stored, okay, at index I to begin with. Then the outer loop will run again. We'll go to I equals 2 and do the same thing. We'll figure out where that second index goes, and the third, and so forth. All right, let's give you an example of this sort algorithm in action. So I've got that same list we started off with here. And for the first few steps, I'm just going to look at big picture. Basically, each time I run through my outer loop, starting with I equals 1 on up the line, I'm going to get everything behind that index in order. Okay, so first time through, the index is the 1, and we're going to get everything less than 1 in order. In other words, we're going to swap the 2 and the 9. Okay, pretty simple. Okay, second time through that outer loop, my index is now 2. And what this whole mess on the inside is going to do is just get everything from 2 and below in order. It's going to take the 8 and put it in the right spot, and then end up with that right there. Okay, as we go further here, let's break this down into a little more detail. Okay, so third time through the outer loop, my index is now 3. And basically what this inner loop is going to do is take whatever's at the third index, in this case the 5, and it's going to put it in the right order. So let's watch that happen here. I need to get my face out of the way. There we go. All right, so let's see what happens. We're going to hold on to that 5 in a temporary variable called val. And then we're going to set our inner loop counter j equal to the I, so equal to 3 in this case. So there's our inner loop counter. Okay, while j is greater than 0, which it is, and what's stored in val is less than the value at j minus 1, okay, which in this case is true. Val's 5, that is less than 9. What we're going to do is we're going to set what's at j, so num set at j to the previous element, in this case the 9, and then we're going to move our j down by 1 and continue that inner loop. Okay, j is still greater than 0, and val is still less than what's at 1 minus j. Okay, what's at 1 minus j is 8. So what we'll do once again is we're going to remove what's at j, okay, and set that to what's at j minus 1, so in this case the 8. And then again, j goes down by 1. And we'll look to run through that loop again. Now in this case, j is still greater than 0, but val is no longer less than what's at 1 minus j. Okay, what's at 1 minus j is at 2. So in this case, what's going to happen is we're going to set what's at j. So the loop's done. We're going to set what's at j to value. We'll set it to that 5 right there. Okay, so all that would represent what happens in the third pass through that loop. Let's run through one more time. Let's take a look at kind of the final pass through the loop. Again, outer loop goes to I equals 4. And essentially what the inner loop's going to do is take what's at I equals 4, okay, as in the 7, and it's going to stick it in the right spot for my loop, shifting everything down. Okay, so we'll store our temporary value 7. J is going to get set equal to I. And we'll compare, can j go down, and is what's below j greater than 7? It is. So we're going to move the 9 up to where the spot j. We're going to move j down by 1. And then we'll do that same comparison. Can I go down? Yes, I can. Is what's in the next lowest spot less than val, which is 7? It is. So we'll move that 8 up. We'll set what's at j to the 8. We'll move j down once again. And then we'll ask the same question. Is 7 less than the previous number 5? It is not. Okay, so my inner loop is over. We'll set what's at j to val. All right, and there we go. My list is sorted. A lot going on there in between kind of the different runs. There's a kind of a mess happening on this inner loop. Again, though, the nice thing about this when it comes to test questions is it's pretty easy to get kind of the state of the array at the end of each iteration through the outer loop. It's easy to get these steps in order, okay, just kind of by putting stuff where it falls. Okay, like I said, this is a lot like the natural way people sort, okay, just in algorithmic form. Just like with the other algorithms, there is a demo of this where you can click through basically this PowerPoint at your own speed, kind of watch it happen. I'd recommend check that out. Get my face back over here. Last thing then is let's talk about advantages and disadvantages of insertion sort. The main advantage is it's kind of natural. Like we said, it's the way people would sort a list if you gave them a list to sort. Disadvantage is it requires more memory, more CPU usage. Okay, it's a little more complicated algorithm, so the computer is going to be storing more things as it goes. It is faster though. Okay, why is it faster? Like we've said a few times before, basically speed for computing comes down to how many comparisons you need to make. Since we're talking a while loop that may not have to go through the entire list every time, like we do in selection sort, there's probably going to be, chances are there's going to be less comparisons. That's why this one will go faster. And as you can see with that same graph we showed the other day, selection sort, kind of our basic sorting algorithm, as the numbers get high, it starts taking a lot longer than insertion sort. Now this is an average for insertion sort. Again, since it's a while loop where you can't tell right off the bat how many times the inner loop's going to run, okay, we could create a list where it runs a maximum number of times and is the same as selection sort. That'd be basically if we were sorting a list in perfect descending order back to ascending order. Okay, the two would tie. Usually that's not the case. That's why an average insertion sort goes quicker. All right, so there you go. That's insertion sort. Like we said, try to walk through that coding demo we have. Give the homework a shot. Again, the goal here isn't to memorize the code for this algorithm. It's, do you understand what's happening? Can you step through it? Okay, if I throw some variations or some extra print statements in there, can you tell what's going to happen? Okay, so give it a shot. Shouldn't be too bad. If you need help, make sure you're getting it. Make sure you're reaching out. Make sure you're seeking us for help here.